Arduino Uno. The Arduino Uno is the board that introduced millions of people to hardware. It runs an ATmega 338P microcontroller clocked at just 16 MHz with 32 KB of flash memory and 2 KB of SRAM. Those numbers are tiny by modern standards. But that is actually the point. Arduino is a microcontroller, not a computer. There is no operating system, no multitasking, no file system. Your code runs bare metal. That means it executes directly on the hardware, one instruction at a time, without anything else getting in the way. You write a loop, and it runs that loop every single time without interruption. That kind of predictability is actually a strength when you are controlling physical hardware. Where Arduino falls short is complexity. You cannot run machine learning, serve a web page, or process video on it. But for reading sensors, driving motors, controlling LEDs, or building simple home automation, nothing is faster to set up. The Arduino IDE is free, the documentation is massive, and the community has answered almost every question you could have. It is the first board most people learn on. And for good reason. Simple, predictable, and backed by the largest hobbyist community in electronics. Raspberry Pi Pico. The Pico is the Raspberry Pi Foundation's take on a microcontroller. But do not confuse it with the Raspberry Pi 4, which is a full computer. The Pico is a small, low-cost chip designed purely for hardware control. It runs the RP2040, a dual-core ARM Cortex-M Plus clocked at 133 MHz, with 264 KB of RAM and 2 MB of onboard flash. The price is around $4. Compared to the Arduino Uno, the Pico is significantly faster, has more memory, and runs on a modern ARM architecture instead of the older AVR platform. It also supports MicroPython out of the box, which makes it much easier for beginners who already know Python. One standout feature is PIO, which stands for Programmable I/O. These are small state machines built into the chip that can generate precise hardware signals independently from the main CPU. That makes the Pico surprisingly capable for tasks like driving addressable LED strips or implementing custom communication protocols. The main trade-off compared to the ESP32 is that the standard Pico has no built-in wireless. There is a Pico W variant that adds Wi-Fi, but it still lacks Bluetooth. For anyone choosing between an Arduino and something a bit more modern, the Pico is a strong option at a very similar price point. ESP32. The ESP32 by Espressif is where things get really interesting. It has a dual-core Extensa LX6 processor running at up to 240 MHz, 520 KB of SRAM, built-in Wi-Fi, Bluetooth 4.2, and BLE, all on a chip that costs around $2. That price alone makes it one of the best deals in the entire dev board market. Compare that to the Arduino Uno. The Uno has no wireless capability at all and runs about 15 times slower. The ESP32 can run Arduino code, MicroPython, or Espressif's own ESP-IDF framework, so you have flexibility in how you build your project. It also has a built-in Hall sensor, capacitive touch pins, 2 DACs, and multiple SPI, I2C, and UART interfaces. For the price, the feature list is almost hard to believe. The one trade-off is voltage. The ESP32 is a 3.3V device. So, if you are connecting it to 5V sensors or modules, you need level shifters to avoid damaging the board. But for any project that needs wireless connectivity, like smart home devices, IoT sensors, weather stations, or remote data loggers, the ESP32 is the default choice. It is easily the most cost-effective connected microcontroller on the market right now, and the reason most IoT hobby projects start here. Teen asks why. The Teensy is an ARM-based microcontroller board built for speed and precision. The Teensy 4.1, which is its most popular version, runs an ARM Cortex-M7 at 600 MHz with 1 MB of RAM and 8 MB of flash. That makes it one of the fastest microcontrollers you can buy on a development board today. Where the Teensy really stands out is audio and USB. It has a dedicated audio library that lets you build synthesizers, effects processors, audio analyzers, and multi-channel mixers with very low latency. It can also act as a native USB device. That means it can pretend to be a keyboard, a mouse, a MIDI controller, or a game controller without any extra hardware or drivers. You just plug it in and it works. Compared to an STM32, the Teensy is easier to get started with because it uses an Arduino-compatible toolchain. Compared to an ESP32, it is much faster but has no built-in wireless. The trade-off is price. A Teensy 4. One costs significantly more than an ESP32 or Arduino. But for projects involving fast signal processing, real-time audio, or custom USB input devices, the Teensy has a loyal following and is genuinely hard to beat in its niche. STM32. The STM32 family by ST Microelectronics is what separates hobbyists from professional embedded engineers. These chips are based on ARM Cortex-M cores. The range is wide. At the low end, you have the M0 Plus for ultra-low power applications. At the high end, the M7 core in the STM32H7 series runs at 480 MHz with a double precision floating point unit, hardware JPEG encoding, and up to 1 MB of RAM. Unlike the Arduino or ESP32, STM32 does not hold your hand. You configure clocks, DMA channels, interrupt priorities, and peripheral registers yourself, usually through STM32 CubeID and the HAL or LL libraries. That complexity gives you something valuable in return. Deterministic real-time performance and industrial-grade reliability. Where the ESP32 might drop a Wi-Fi packet or have timer jitter, an STM32 will execute with microsecond precision every time. That is why you find STM32 chips inside drones, industrial controllers, medical devices, and consumer electronics. Not sitting on a desk as a hobby project, but inside actual shipping products used by real customers. The learning curve is steep, and the documentation is dense. But if your goal is to build something production-ready, STM32 is the path most professional embedded engineers take. Raspberry Pi. The Raspberry Pi is not a microcontroller. It is a full single-board computer, and that distinction changes everything. The Pi 4 runs a quad-core ARM Cortex-A72 at 1.8 GHz, supports up to 8 GB of LPDDR4 RAM, has USB 3.0 Gigabit Ethernet, dual micro HDMI outputs capable of driving 4K displays, and runs a full Linux operating system from a micro SD card. Compare that to the ESP32 with 520 KB of RAM. The Pi 4 has over 15,000 times more memory. That gap explains the difference in capability. A Pi can run a web server, a database, Python scripts with full NumPy and OpenCV libraries, a web browser, and even a full desktop environment with a graphical interface. What it cannot do well is real-time hardware control. Linux is not a real-time operating system, so GPIO timing on a Pi is inconsistent and unreliable for precision tasks. You would not use a Pi to generate a precise PWM signal for a motor controller, but you would absolutely use one to process a camera feed, host a local API, or run a TensorFlow Lite model for image classification. Think of it less as a dev board, and more as a tiny, hackable Linux computer that happens to have GPIO pins on the side. BeagleBone Black. The BeagleBone Black is probably the most underrated board on this list. It runs a 1 GHz ARM Cortex-A8 with 512 MB of RAM and 4 GB of built-in eMMC storage. Like the Raspberry Pi, it runs full Linux. But the BeagleBone has something the Pi simply does not have: 2 onboard programmable real-time units, or PRUs. These are 200 MHz 32-bit processors that run independently from the main CPU. They execute bare metal code with deterministic, nanosecond-level timing. That means you get the best of both worlds on a single board: a full Linux environment for your application logic and networking, and microcontroller-grade precision for your hardware control layer. No second board needed. It also has 65 GPIO pins compared to the Pi's 40, more analog inputs, and multiple PWM outputs natively available. BeagleBone is widely used in CNC machines, robotics, industrial automation, and any application where Linux flexibility and real-time hardware precision must coexist on the same device. The community is smaller than the Pi's, and the documentation is denser. But for engineers who know exactly what they need, the BeagleBone is genuinely hard to replace. NVIDIA Jetson Nano. If the Raspberry Pi is a tiny Linux computer, the Jetson Nano is a tiny AI computer. It packs a quad-core ARM Cortex-A57 CPU alongside a 128-core Maxwell GPU, with 4 GB of LPDDR4 RAM and 16 GB of eMMC storage. The GPU is the entire point of this board. The Raspberry Pi 4 has no meaningful GPU compute capability for machine learning workloads. Its theoretical AI performance sits at roughly 0.1 TOPS. The Jetson Nano delivers 472 GFLOPS of FP16 compute. That is enough to run real-time object detection with YOLOv 3, pose estimation, facial recognition, and semantic segmentation, all processed locally on the device with no cloud dependency whatsoever. It runs Jetpack, which is NVIDIA's Linux-based SDK, with full support for CUDA, TensorRT, and DeepStream. The trade-off versus a Raspberry Pi is cost and power consumption. The Jetson Nano is significantly more expensive and draws considerably more electricity. But if your project involves a camera and a neural network running in real time, there is no real comparison at this price point. The Jetson Nano sits in its own category for accessible edge AI development. Google Coral Dev Board. The Google Coral is another option for running AI at the edge, but it takes a completely different approach from the Jetson Nano. Instead of using a GPU for neural network inference, the Coral uses Google's Edge TPU, which stands for Tensor Processing Unit. This is a purpose-built chip designed specifically to run TensorFlow light models with maximum efficiency and minimum power draw. The Coral Dev Board runs a quad-core ARM Cortex-A53 at 1.5 GHz with 1 GB of RAM, plus the Edge TPU coprocessor, which delivers 4 TOPS of inference performance. That is actually higher raw throughput than the Jetson Nano on supported model types, while drawing significantly less power, usually around 2 watts under full load, compared to the Jetson's 5 to 10 watts. The trade-off is flexibility. The Jetson Nano supports CUDA and can run a wide range of AI frameworks and model architectures. The Coral only runs TensorFlow light models, and those models must be compiled specifically for the Edge TPU before deployment. So if your project fits within that ecosystem, the Coral is faster and far more power efficient per inference. If you need broader framework support, custom model architectures, or on-device training, the Jetson is still the better pick. Tessel 2. The Tessel 2 takes a completely different approach from every other board on this list. It is built for JavaScript developers, not embedded engineers. It runs a MediaTek MT7620N processor at 580 MHz with 64 MB of RAM, running a lightweight Linux environment with Node.js built in from the start. That means you write your firmware in JavaScript. You use NPM packages directly. You interact with sensors and motors, a JavaScript API. No C, no Python, no new development tools to learn. It also has built-in Wi-Fi, USB host support, and 2 dedicated module ports that accept plug-and-play hardware modules for things like GPS, Bluetooth, ambient light sensors, and servo motor control. Compared to the ESP32, the Tessel is far less power efficient and more expensive for what you get in raw hardware. Compared to a Raspberry Pi, it is more constrained but faster to prototype on if JavaScript is your primary language. The Tessel never captured widespread mainstream adoption, but it represents a real and valid philosophy. The best dev board for any developer is the one that speaks their language. For full-stack web developers who want to build hardware without learning an entirely new toolchain, the Tessel lowers that barrier dramatically. Particle Photon. The particle photon is less about raw specs and more about what surrounds the hardware. It runs an STM32F205 ARM Cortex-M3 at 120 MHz with 1 MB of flash and 128 KB of RAM. Those are solid microcontroller specs, in the same ballpark as a mid-range STM32. It has built-in Wi-Fi through a Broadcom module and is programmed through Particle's cloud-based IDE. But what makes it genuinely different from everything else on this list is the Particle device OS and cloud platform. Every photon is automatically registered to your Particle account. It can receive over-the-air firmware updates, publish sensor data to the cloud, subscribe to remote commands, and be monitored across an entire fleet of devices. All out of the box, with zero additional infrastructure setup. Compare that to an ESP32, where you would need to build all of that yourself. OTA update servers, fleet management dashboards, cloud messaging pipelines, device monitoring systems. For a hobbyist working on a single device, that overhead might not matter. But for a startup shipping 500 connected products to paying customers, Particle eliminates months of back-end engineering work. It bridges the gap between prototype and finished product better than any other board on this list. Anyway, I also made some other cool videos too. Don't forget to watch them later. Okay,